Thank you very much. Great to be here today, and it's my pleasure to be able to present the results of the REFLECS study. On behalf of my co-investigators, I'm unfortunate that my junior faculty, Francois Haddad, wasn't able to attend today, so I'm stepping in his place. I'm also presenting on behalf of all the investigators, but more importantly, the patients and the participants who volunteered for the REFLECS trial. All of my financial disclosures can be found on my faculty profile website at Stanford University. We know that heart failure is a growing burden in our healthcare systems and in our society. The prevalence is increasing. There remains substantial morbidity and mortality with this disease, and the cost and strain on our health system is exorbitant. Strategies that can help with screening, diagnosis, and more efficient management may be able to improve the efficiency of clinical care delivery for us physicians, improve the ability to get through our health system evaluations by our patients, and then finally, hopefully decrease the burden on our healthcare system and our costs. Seismocardiography has been used for many, many years to evaluate various cardiac functions. It's a non-invasive technique for assessing both heart motion using accelerometers, but also the angular velocities of heart motion using gyroscope technologies. Signals from these sensors can be obtained in multiple planes, and then correlations can be made with various cardiac parameters, including cardiac contractility, strain, and various cardiac intervals, often associated with valve opening and valve closure, as shown in the graphic. These technologies, the accelerometer and the gyroscope, collectively called microelectromechanical systems, are embedded in the smartphones that we carry with us every single day. These sensors can be used to collect signals that can be analyzed to show correlations to cardiac systolic and diastolic motion, and then can be related to traditional things that we think about in cardiac assessment, including S1, S2, S3. But more importantly, we can look at the amplitude, we can look at the area under the curve, we can look at time intervals to get a better understanding of differences between heart failure patients and patients who do not have heart failure. CardioSignal has been developing this technology for a number of years. These signals are obtained by putting the smartphone on the chest. It is commercially available in the EU for AFib detection, and a number of other cardiac indications are being evaluated at this time. In the REFLECS trial, we wanted to look specifically at patients with heart failure. The primary aim was to test whether or not signals from the smartphone-based microelectromechanical sensors, the accelerometer and the gyroscope, can differentiate patients with heart failure from controls. This study was conducted in 3 centers in Finland and the United States. It included 2 types of heart failure participants. One were patients who were enrolled or admitted to the hospital with acute decompensated heart failure, and those patients were compared with controls. We also looked at a group of patients with heart failure who were stable, being seen in heart failure clinics, who were also compared to controls. The diagnosis of heart failure was made by the local site investigator using standard clinical pathways and assessment approaches. Controls were patients who did not have a history of heart failure or any major signs or symptoms of heart failure, who were being referred to cardiology clinics for evaluation for coronary artery disease. The primary measures that we pre-specified were the area under the curve and accuracy for detection of heart failure. We used logistic regression and bootstrap aggregation to develop the diagnostic algorithms that I'll show you. And we predefined a minimal level of accuracy for the detection of heart failure at 80%. In total, we enrolled over 1,000 participants. 22 were excluded, as you can see, and 1,003 were included in the analytic cohort. In total, 217 of these participants had heart failure. There were 786 controls. There were 174 who were evaluated in the acute decompensated heart failure state, and 172 were evaluated in the outpatient stable state. You'll see that 174 and 172 add up to more than 217. That's because some patients were evaluated in both the hospital and in the outpatient state. The signals from the gyroscope and the accelerometer were assessed using a Galaxy 9 iPhone by placing the iPhone on the chest with the patient in the supine position, lying still for just 2 minutes. The signals were uploaded to a secure platform in the cloud. Analyses were done in multiple axes. Standard filtering and quality control was applied to the data. The algorithms were developed using initially a derivation cohort, which included 50% of the cohort of heart failure participants and similarly matched controls. The heart failure state-dependent models were developed using logistic regression. They were then validated in the remaining cohorts, and then bootstrap aggregation was applied to independently reevaluate the models 10 times over. The data extraction included, as I mentioned previously, the AUC for the ROC curves and traditional diagnostic metrics for medical devices. We looked at the individual run-specific analyses for consistency. We also performed subgroup analysis based on age, sex, body weight, and other factors. And then we were also interested in looking at how the accelerometer data performed compared to the gyroscope data alone. Here you can see the baseline demographics and clinical characteristics of those patients with acute heart failure, outpatient heart failure, and the controls. As expected, there are many differences between these three populations. Those with heart failure were older, they were more often male, they had higher body weights, they had more cardiovascular comorbidities, they had BNPs that are shown here that were elevated. 3/4 of the patients had heart failure with reduced ejection fraction. 1/4 had heart failure with preserved ejection fraction. And the median LV ejection fraction is shown here at 39% and 48% in the outpatient heart failure cohort. The primary results of the REFLECS study are shown here, that the bootstrap algorithm for heart failure classification or discrimination was robust. In all heart failure patients, the AUC was 0.95. This was similar in patients with acute decompensated heart failure and in patients with stable outpatient heart failure. On the right-hand side are the data looking just at the gyroscope signals in the models and the accelerometer signals in the models. And you can see here that the gyroscope signals tended to be better than the accelerometer signals with an AUC of 0.87 compared with the accelerometer data of 0.64. But no difference was detected in those patients with and without atrial fibrillation. A little bit of concern because of the irregular heart rhythm that often is seen with atrial fibrillation. The other common test parameters for the acute heart failure population, the stable outpatient heart failure population, and the overall population are shown here. The AUC data, as you've seen on the previous slide. Sensitivity overall was 0.85, specificity 0.90, and similar in the two heart failure cohorts. The accuracy overall was 0.89, well above our predefined threshold of 0.80. Positive predictive value of 0.62. And importantly, the negative predictive value high at 0.97. These results were also similar in the subgroup analyses that I mentioned previously, defined by older and younger age, body mass index, and other key parameters. There are some important limitations in the REFLECS study. One, this trial was performed in 2 academic medical centers in Finland and the United States. Echocardiography was not performed in all of the control population, so we may have included pre-heart failure stages that could influence the results, particularly with the cardiac motion analyses. As I showed you, there are key differences in the demographics noted between the controls and the heart failure. That's expected, but despite the bootstrap aggregation, validation, and sensitivity analyses that we performed, we didn't think that this confounded or biased the results. These data were pulled from 3 different centers in 2 different countries, but we used the same signal acquisition protocols and had very similar inclusion-exclusion criteria at the centers. In summary, I believe the REFLECS trial shows that simple smartphone-based assessment of cardiac function by motion sensors embedded in the smartphone technology is feasible. That these motion sensor signals can enable the detection and discrimination of heart failure in patients with both acute and stable heart failure compared to controls with high discrimination with AUC of 0.95 and an accuracy of 89% and a negative predictive value of 97 or 98%. These results, as I mentioned, were consistent across different heart failure states. And I believe that with further evaluation, particularly in broader patient populations, that motion sensing capability could potentially enable simple remote assessment of patients in the future. I want to thank again all the participants who volunteered for the REFLECS study. Their contributions and commitment to the program was invaluable, and all of the site investigators and coordinators who helped collect these data. Thank you very much. Look forward to some questions.
Thank you. Thank you so much. I guess we have first question on the mic, number 3.
Ken, thank you. That was fantastic. I was wondering if you could speak at all to any features of the robustness of the operational application. Candidly, I'm not sure I could balance a smartphone on my chest for 2 minutes. And more importantly, just thinking about some of the patients we see in terms of levels of, I guess, education, sophistication, robustness in terms of placement of the phone. So someone who might have it up at the sternal notch versus down at the diaphragm, anything like that you might be able to share?
Yeah, so I didn't hear the first part. So you want to understand the different patient populations in terms of body habitus and how likely they are to use the technology?
Very candidly, thinking of a 65-year-old woman attempting to balance a smartphone on her chest for 2 minutes.
Yeah.
And to be fair to her, I'm not sure I could do it.
Yeah, a critical point, and it's why I made a comment at the very end, is that one of the things that we're looking at now is how do we test this kind of technology as we're thinking about all technologies in what I call the wild. It's easy to do this in a controlled setting, in a hospital or in a clinic. But I see the value of these technologies, this technology, as well as the technologies that you've heard about already this morning in this great session, is how can we do it in the wild? How can we do it in patients' bedrooms? How can we do it in patients' living rooms and kitchens? And I think that's where the spirit of your question is getting at. Now, I'm from Silicon Valley, and we have a lot of people, especially the elderly, who love technology. And so that is not universal. But I think that with the common use of smartphone technologies, we saw no problems in the clinics when we had people lie down, put the phone, and we put the phone on their chest, but there was no problems at all collecting the signals in that situation. Most people were able to lie flat for just 2 minutes. They weren't nervous. We were able to assess the signals with high quality. We were more concerned about people who may be more overweight. We didn't see any difference in the signal quality or the diagnostic parameters, so that was very reassuring. But I agree, we need to look at this in broader patient populations.
Thank you. We have another question.
Thank you very much for the interesting talk. I'm asking myself 2 questions without thinking about a special diagnosis, but do you think this technique could also be applied in other diagnoses than heart failure? And the second question is, if there is such a good discrimination between heart failure and no heart failure, do you think there could even be a correlation between a certain percentage of ejection fraction? Like you could do a graph and say this signal means 10%, this one means 30%, and so on?
Yeah, great questions. Yes, I believe this technology can be used to evaluate different cardiovascular conditions. One, as I mentioned, it's already been evaluated in atrial fibrillation and has received regulatory approval and is commercially available in Europe. It's also undergoing evaluation for coronary artery disease, considering evaluation for valvular disease, particularly aortic stenosis. In your question about heart failure, we haven't yet been able to go back and look to see differentiation at a very granular level for different types of heart failure. I showed you that 3/4 of the patients had reduced ejection fraction and 1/4 had preserved ejection fraction. We saw no difference in the diagnostic capability of the algorithms from the phone for those populations. But what we're very interested in is ejection fraction, the severity of heart failure. Most of these patients were class 2, class 3 when they were admitted to the hospital. And then importantly, with the great interest now in things like amyloid cardiomyopathy and new therapies for that disease state, including late-breaking clinical trials with new therapies here at ESC, we're looking to evaluate in specific types of heart failure as well.
Thank you. The questions are piling. Just one more question from the audience, please.
Thank you very much. Michael Rini from University College London. Fascinating study. I would be curious to know a little bit more about the features that you have used, extracted from the signals, whether they were hypothesis-driven, data-driven. So some information about the features that you have used for discrimination.
What features were used for discriminations? What features from the signal here?
Yeah, a variety of different features were used in the models. As I showed on the schematic, we looked at features that were associated with cardiac contractility. We looked at features associated with cardiac strain. We looked at features that were associated with specific time intervals, both in systole and diastole. It's those features that are then put into the model for further assessment. We have a paper that's coming out that's going to be describing more of this in the near future.
Thank you for this excellent study. I haven't read it anywhere. Have you published it?
No, unfortunately not.
Would you think of submitting it to European Heart Journal Digital Health, which is a sister of our journal?
We've already submitted it somewhere else, trying to get it published simultaneously with these meetings, but weren't successful. But we tried.
Okay. I find it important because it's a multicentric study from different nations, from Finland and from USA. So it's time for conducting such studies internationally, because the data has to have veracity as long as velocity, So it has to be variable. in the age of digital twin. So it's time for conducting such international studies. And one more question. How can you, as a physician, how can you convince me to use the smartphone for detecting the worsening of heart failure instead of using a stethoscope which can detect ejection fraction?
Yeah, I think that the future state is going to be the ability to aggregate multiple streams of data as we evaluate patients, both face-to-face in the clinic, but as we're evolving to more virtual care, particularly for our patients in rural communities. I think that we now have the ability to get data from electronic stethoscopes, from smartphones, from wearable devices. You've seen from history tools and applications. What we need to be able to do within our health systems is aggregate that data in real time, in simple ways that the clinicians can act on it real time in shared decision making with their patients. So I look at all of this data as complementary, not exclusionary. Thank you.